How can we create exponential variate from uniform variate? Exponential variate means exponential distribution, random numbers from exponential distribution from a given uniform, normalized uniform variate or random number distribution. Well, what is an exponential variate? What is a uniform variate first? So here, if we generate random numbers, say from 0 to 1, and if we see the frequency distribution, then it will be uniform. That means if we check the histogram, the heads of the histograms will be equal, and in practice more or less they are equal. So it's a uniform variate. Okay, and let us call it U, and the numbers are from between 0 and 1. This we can write a program to create these pseudo-random numbers, uniform pseudo-random numbers between 0 and 1 through linear congruential generator, or we can use a standard uniform random number generator from NumPy or basic core Python. Well, from this we want to create an exponential distribution. What is an exponential distribution? It looks like it's an exponential really, and it will be like this. Okay, so if you see the frequency distribution, it will be the bars will be, the heads of the bars will be this, they will follow this exponential form. So this is an exponential distribution. Usually exponential distribution is written as lambda e to the power minus lambda x. So x is the variate name of this variable here. Here u is the name of the variable, capital U. Usually in statistics we call it capital. We reserve capital U or capital X for the name of the variate, and then we can think of well, up to some distance, up to, here is the value. So the values are written as small letters. Okay, so this will come from U to X. This is our task. We'll create an exponential variate which is written as X, and which we will create from the uniform variate which is written as U. Well, so that means we'll create random numbers up to certain, say, small u, for example, and the cumulative distribution function. That means the probability of getting the number up from 0 to up to certain, say, u will be something, and that will correspond to some value from, say, 0 to up to some certain x. We'll find out what u corresponds to what x. Okay, and you will see the, if you take the cumulative distribution function of this, that means up to from 0 to 1, the total integration, that will be 1. And here also, if we write, say, 0 to infinity, because here the range is from 0 to infinity for an exponential distribution. And if we write lambda e to the power minus lambda x and then dx, and it will be equal to lambda and minus 1 by lambda e to the power minus lambda x and 0 to infinity. And if we put the values in limiting values, then it will be e to the power minus infinity will be 0, and then minus 1 plus, and then it will be 1. So it is normalized. That means in the entire interval the total probability is 1. So it will correspond to total area under the entire curve is actually total area under this entire curve. Okay, so that's what that should correspond. Well, if we look at the CDF of this, that means cumulative density function, then it will be like this. It will be like, if we plot x versus this CDF, it will go like this, and eventually it will be close to 1. Why? That's because say if we integrate from 0 to x, some value of x, say 0.6, say for example, the total area will be somewhere say here or so. If we integrate up to say some 0.9 or something, it will be something here, like that. And so eventually if we take more and more areas, so the total integral up to the cumulative integral up to from 0 to up to that point will be bigger and bigger, and eventually it will touch the line at 1. So that's the idea. So the thing is that what is the cumulative density function? So cumulative density function, if we write as p for this x variate, x is the exponential variate. If we write p, and if we write x less than equal to x, that means up to some x value, x is the value and x is the name of the variate, so and p is the cumulative density function. So that is equal to 0 to x lambda e to the power minus lambda, let's change the name of the variable, x prime function, and it is dx prime, right? So if we integrate this, of course it will be 1 minus e to the power minus lambda x. So the cumulative probability distribution for the exponential variate is 1 minus e to the power minus lambda x. Now what it will correspond to, this p value, this will be p x less than equal to x, that means from 0 up to value x. What is this x? This x is, how do we get x? We get x from u, right? We get x from u. That means we think of some transformation. We think of some transformation t u equal to x, right? So how do we get this transformation? So that is the question. So in fact we can write we can find out, that means for this value x, basically for this value x, we want to know what is the value of u that will correspond to this value x, right? So for that we use this transformation du equal to x. We have to determine this transformation. Rather we do the opposite thing. That means we can write u equal to t inverse x. So it's a inverse function basically. Okay, so it's the inverse transformation. So it is the inverse transform. So we have to find out this inverse transformation function, right? So basically we have this uniform distribution. We have this uniform distribution between 0 and 1, and this u, I'm sorry, so this u will be somewhere here, say for example, and this is nothing but t inverse x, because u is t inverse x, right? Okay, so what is this t inverse x? Well, and since it is u, and so for this uniform distribution, this cumulative value is also u, because it is normalized. Okay, so suppose it is 0.7, say, suppose u equal to say 0.7 or something, so the cumulative distribution function is also 0.7. So that means we can think of u is equal to 1 minus e to the power minus lambda x. So I mean you can write it as, say, x, for example. Since we are writing capital U, we can write it as capital X. If we write it small u, you can write it small x. Okay, let me write it as capital U. Okay, so so this is this. Okay, so now we can write 1 minus u equal to e to the power minus lambda x. That means log of 1 minus capital U equal to minus lambda, say, x, right? So that means x is equal to minus of log of 1 minus u by lambda. So hence we get the reverse or inverse transformation. That means we get now the value of capital X. X is the name of the variate, but we can easily write small x and small u here. So we can, this is the inverse transformation function. So this is the inverse transformation function. Okay, that means we have now here determined x given the value of u. Okay, that's what we want. Okay, and we implement this in computer. If we take take lambda equal to 1 for simplicity, so then x equal to simply minus log of 1 minus u. So that's what we are going to implement in computer. Okay, and then we'll see whether the distribution we make will be exponential or not. Well, so let me go to the Jupyter notebook. Let me first import numpy as np. Okay, so next is we need to import matplotlib dot pyplot as plt for plotting. Okay, so now we need to create the uniform distribution, so some numbers from uniform distribution. So let me write it as u equal to, you can write it as a capital U, say, or the values if you want, you can write small u, name doesn't matter. So np dot random dot uniform, and if you want to create from 0 to 1, we can write 0 to 1, and then size equal to some value, let me call it some capital N. So before that we write capital N equal to say 100,000, 1 lakh numbers. So we can create this 100,000 numbers, right? It is done. Next, what we can do? Next is nothing. If you want to create x equal to np, what is the transformation function? Simply minus of np dot log and 1 minus u. So done. So the exponential the numbers from exponential distributions are done. Just that. Okay. So we have used this transformation function. That's it. So how do you know this is becoming exponential? That means x is the exponential variate. How do we know? Just plot. Let me plot them. plt dot hist, and if we write x and say now we do write bins equal to 50, that means we are creating 50 bins, for example. And for a good plot we write h color equal to black, so that we can see the histograms properly. Okay, so that's it. If we run this, it will show you the distribution, which is, you can see this is exponential. I can write it as plt dot xlim to make it more better, to some value, say 8. Okay, so it plots from 0. So it is very much exponential. But how do I know whether this is matching with the exact exponential function? Okay, so for that we'll plot something else with it. One thing you see when you write this, when you run this, it will show you the numbers, show you some arrays. First set of arrays, it is the they are the frequencies, that means on the y-axis values. Okay, and the next set of arrays, these are the bins, and these are the bins which starts from here, left end of one bin and the right end of another bin, then it will be the left end of the next bin, and this will be the right end of the next bin, and so on. So these are the bin boundaries. Okay, and also it has created something else, a list of 50 patch objects, which we don't need. That means it has actually given you a tuple of 3 things. First, frequencies, then the array of the bin boundaries, and then something else. Well, so now if we write, say for example, frequency, and then say bins, that means bins will consist of the bin boundaries, and something else which I name, say, extra. Okay, if we write this plt dot hist and x and bins equal to say 50 and blah blah blah, and h color, you don't need to write this now. So if we run this, I don't want to plot this, but it will, the frequency will be, the first part will go to frequency, the second part will be the bins, and third part will be the some extra we don't need. Sometimes we write as anonymous variable as this when we don't want to write any name anyway. So it is automatically plotting here. I don't need this plot, but anyway I need this information of frequency and bins. Well, now I want to calculate the midpoint of the bins. So bin mid, because the histograms, I want the midpoints of these bin bars, and then I will join the bars and I will see whether this is exponential. I want to plot an exponential function through this, and to see that whether it is matching with the bin bars, bar heads. Okay, so bin midpoints are actually, bin midpoints are here actually on the x-axis, here on this x-axis. So exactly what I need is that I just need this value and this value and the average of this value, and then this value and this value, and then the average of this value, and so on. So what I do is that for every bin, if I want to do, then I need the bins, and I start from the first until the before the last one I want to go, and then I want to write bins. These are slicing, right? And 1 colon, that means one set of bin widths which are from beginning to before the end, and one is from, and the next one is from the second value, that means from 1, and it will go until the last. So the, if I add these two sliced values, sliced arrays, and multiply this with 0.5, 0.5, that means this will create the array of the midpoints of the bins. Okay, so these are the midpoints. Now I want to create the width, bin width. What is the bin width? Bin width is just this gap, right? This gap. You can easily calculate. You can say, for example, write bins of 1 minus bins of 0. So that will give me the width of each bin. Width of each bin is same. Okay. Now I want to create the theoretical frequency. That means I write it frequency theory. Okay. So what will be that? Frequency, theoretical frequency will be so np.exp, and which will go through the midpoints of the bins, right? I want to draw this. I mean, that means this point, this point, this point, this point, and I need these points for as x-axis, and with the with that points I want to create an exponential function. So exponential function is, instead of writing np.exp minus x, I want to write np.exp, and it will be minus bin midpoints. I want to write I want to put this. So the, as if the function goes through the midpoints of, I mean the for each midpoint, through each midpoint the function will go. Okay, for each midpoint the y values will be given by this function. Okay, so you mean you understand what we exactly mean. Okay, so this one, and to match with this I have to multiply with bin width, because to match with the x y axis, right? Bin width, and also I want to multiply this with size, that means n. That means it will give me the exact frequency values. So frequency values are not by the counting, it is by the exponential function, and the exponential function goes through all the midpoints, and the I multiply with bin width, and then the size, total size. That means it will I will actually get these numbers. These are the numbers of points between this and this. Okay, first the exponential, this point will come with this exponential, this will be the exponential thing, then the width, and the n is the total number. Out of total number, how many are here? Okay, so these are the, this will create the theoretical frequencies. Okay, okay, and now I want to plot this. plt.plot, and then bin mid, say bin mid, and frequency theory. Okay, and I want to plot with this with, say, line, so automatically it will plot with lines. Okay, and maybe I want to plot this with lines and points, with lines and points. Okay, and then next we, along with this, now the histogram again I plot hist, then x, then bins equal to 50, then h color equal to black, and this. Okay, now I'm plotting this histogram along with the theoretical formula, but we have to rescale this, because we have to multiply this bin width and the total numbers. That means it will give you the exact values. Okay, so let me now run it. Okay, okay, here it is here, and also let me plot this with plt.xlim, say 0 to say 8, for example. Okay, and well, let me plot it with the color c equal to, say, red, and here say c equal to blue, b. Okay, let me run this. Oh, c equal to blue, and let me run this. Oh, it's not taking. Well, let me write it color. Yeah, okay, so here it is. So the bars are by the transformation that we are getting from the uniform random numbers, and the red line is the theoretical curve, and the points are basically just the midpoints of those bars, head of the midpoints of those bars that we have calculated. Okay, so here is the thing. Thank you.